About two families of determinantal processes, one on C and one on D. So this is a work of Shirai that we adapted with Nizar Demni from Rennes. And so he considers what is called the Landau-Hamiltonian on C. It has a discrete spectrum, which is n, and each eigenspace is a space of polyanalytic functions that are square integrable with respect to the Gaussian measure. So this means nth eigenspace is L2 of the Gaussian weight on C. Intersected with, so I said polyanalytic functions, it means d bar n of f equals 0. So if you take d plus 1. So if you take n to be 0, you have holomorphic functions that are square integrable with respect to the Gaussian weight. Yes? And so this is a huge family of determinantal point process. So why determinantal point process? Because you can look at Kn to be the kernel. So let me call it En, kernel of the orthogonal projection on to En. Yes, so and if you have the kernel of an orthogonal projection, this is a kernel of a determinantal point process. This is called Marquis-Soshnikov theorem. And so you have a huge family, and the first properties you want to study, so first the average number of particles inside a disk, for example, or this is easy to compute. This is just you integrate the diagonal of the kernel. What is a little bit more difficult is the variance of the number of points in a disk. So, and the theorem says that the variance with respect to Kn of the number of points in a disk of radius r is asymptotically, when r tends to infinity, a constant that depends on n divided by r, and for me it will be a constant depends on m over 1 minus r as r tends to 1. Okay, this is our theorem because we have an analog of the Landau operator on the disk, and we have Bergman polyanalytic space, and this is our theorem. Thank you.
Thank you. So next is Arista and Benassi should come prepared. No. Oh, okay. Well, in these 3 minutes, I would like to introduce a nice relation between loopy race walks in 2 dimensions and random matrices. So let's start. Consider a random particle inside a simply connected domain omega. So the particle starts in a reflecting boundary in blue, and it runs until it hits a reflecting boundary in blue, and it runs until it hits an absorbing boundary in red. The distribution of the hitting point is well known for many examples. For example, in the first case, it's just the folded Cauchy density, and in the second case, is the well-known Poisson kernel in the unit disk. For more than one particle, consider the same setting, but now the motion of the particles is constrained to a particular type of interaction. The interaction between the particles is the following. Paths with larger indices will not intersect the loopy race part of the previous one, so there is a type of repulsion property between loopy race paths. So under this type of interaction between paths, ask you the following 2 questions. What would be the joint distribution of the end hitting points? And the second, what would be the joint distribution of the end hitting points if I consider the limit when the end paths start at a single point in the boundary? Well, it turns out that the heating points should behave as eigenvalues of random matrix ensembles. And the main reason is that this type of non-crossing probabilities between loop erase paths are given by determinant formulas, which are a generalization of the classical Carling-MacGregor formula for non-intersecting one-dimensional diffusions. Now, consider the same problem, but now our particles move in a non-simply connected domain. So for example, here, consider n Brownian motions inside an annulus. So again, the particles start in the blue boundary, which is reflecting, and they run until it hit the absorbing boundary under this type of non-interaction between loop erase paths. We will see that the heating points should behave as the eigenvalues of the circular unitary, the circular orthogonal ensemble, or COE for short. And thank you very much.
So Constanza and Andrew, please come here. Andrew.
Thank you. Okay. May I go? Okay. So we would like to study the Hermitian matrix model, and we're interested in its phase diagram. That is, we want to know what happens. So you see here the partition function of the Hermitian matrix model. We want to know what happens when we change the coupling constants, so which are these parameters t. So it has been proved that if you interpret the parameters t as times, the partition function rescaled in this way is a tau function for the Toda lattice, which you can see reassumed here. So specifically, we are going to interpret the two parameters, an and bn, that appear in the Lax operator as order parameters for our model. And specifically to this partition function, we see that they have initial conditions, as you can see there. Notice that an of 0 is 0. So we focus on the reduction when it's 0 always. This corresponds to the Hermitian matrix model with even times only. That's because if you look at that reduction, you'll see that the differential identities with odd times are actually void. And so we conjecture that we actually know what's the solution of the Toda lattice in this specific reduction. So if we look at the parameter capital B, which is just Bn squared, we conjecture that the Toda identities for the even times just look like this, where these are suitable function of the Bn's. And this we have actually proved for times up to T10, so T2 to 40, 68, and T10. And the solution of something like this can be given in a recursive form. So this is an explicit solution, okay? It's a recursive form, but still it's explicit. So I've told you that we want to know what happens when we vary the parameters. And if you think of the thermodynamic limit in a statistical mechanical sense, this should be equivalent to the continuum limit of the Toda lattice, given the relationship between the two systems. So if you do the continuum limit in the right way, which is described here, what you find out for the recurrence relation I mentioned before is this cubic here, where x is just the continuum equivalent of n. The capital T's are the rescaled times, and u is rescaled capital B in the continuum limit. So since it's a cubic, for certain choice of these parameters, and of course I've put all the other times 0, so I'm looking just at the first 3 times, for certain values of these time parameters, this is a cubic, so u will be multivalued, okay? So if you actually plot the value of the discrete field Bn, rescaled against the cubic, what we see is that this multivaluedness is resolved by something that really looks like a dispersive shock wave propagating in the space of coupling constant. And since B is like the order parameter of our model, we interpret this as a new type of phase transition. And that's it.
Thank you. So, Andrew, Philip, please come. Okay, go.
All right. Yeah, so my name is Andrew, and I would like to introduce my poster on the supercritical regime for the kissing polynomials. And everything here and in my poster is joint work with Guillaume Silva, who is at the University of Michigan. So first of all, the kissing polynomials are just orthogonal polynomials, which are orthogonal with respect to, well, to this weight. And so you should notice that there's an independence, and also the weight is complex valued. So because the weight is complex valued, there are certain questions that are quite, well, not quite easy, but relatively easy in the real case, a real positive case. And here, the questions we want to answer are, do these polynomials exist? And where do their zeros live? So Alfredo has shown that for lambda less than a certain critical value, as n goes to infinity, these zeros accumulate on a single arc connecting -1 and 1. And this is in this first picture here. So you see the zeros, as n goes to infinity, will start to look like this. And in that same work, he showed that for lambda larger than this critical value, they seem to split and accumulate on 2 arcs, which are symmetric with respect to the imaginary axis. So the whole point of what I present in my poster is proving that this situation is actually correct. And we do this in the usual way with Riemann-Hilbert techniques. And as we saw in Professor Itz's talk, a key step here is to construct what's known as a global parametrics. And in our case, the global parametrics is not in a standard form, so we construct it in a different way. And one of the consequences of this construction is that there are certain values of this parameter lambda for which the odd degree polynomials will no longer exist. So if you want to learn more, you should come to my poster, or if you just want to learn why they're called kissing polynomials, I can tell you that as well. So thank you.
Thank you. So Philip is ready, and Fabio, please come. Fabio.
So I'm going to talk about moments of some discrete orthogonal polynomial ensembles. This is joint work with Fabio and Neil O'Connell. It's sort of motivated in part by the work that Fabio is about to present next. What the discrete orthogonal polynomial ensembles will consider, see this well-known measure where the delta n is the Vandermonde determinant, and this can be written in terms of the first n orthogonal polynomials. So we can write this measure in terms of those first n orthogonal polynomials, and we can write the one-point function using these polynomials. So we'll look at some examples of these examples of measures. So in 2005, Ledoux calculated, so it's more natural to consider, rather than the pure moments, the factorial moments. Ledoux calculated these for the moments of the one-point function for the Charlier and the Meixner ensembles, and we added the Krawczyk. And these can be rewritten in the Charlier, and a special case of the Meixner when it's orthogonal with respect to the G-metric rather than the negative binomial. They can be written as 3f1 and 3f2 hypergeometric functions. And our main results come when we, as we saw, the Poissonized Plancherel, if we Poissonize the Charlier, then we get a very nice formula. And likewise, when we negative binomialize a special case of the Meixner, we also get a very simple formula. These satisfy some nice polynomial properties. They satisfy 3-term recurrences. The Meixner is a Legendre polynomial, and the Poisson is an integral of a Legendre polynomial, so they also satisfy some nice ODEs. I'd be interested if you recognize some of these functions that are on my poster, and maybe you could see some links that we haven't. Okay, thanks very much.
Thank you. So, Harini, please come. And now is your, please take the mic.
Okay. Yes, we have seen that there are natural links between classical ensembles of random matrices and classical families of orthogonal polynomials. And this work is about a sort of transversal point of view and different connection between random matrices and families of orthogonal polynomials. So there is, of course, a lot of attention, a lot of work have been done on moments of random matrices. So if you consider a matrix X of size n, you raise it to a power k, where k is a positive integer, and then you compute the expectation. And there is a lot of work when you consider matrices of finite size n or large size. So especially for the classical ensembles, Gaussian, Laguerre, Jacobi unitary ensembles, in some sense we can say that everything is known about this moment as a function of the size of the matrix. So for instance, the paradigmatic example, the GUE, in that case, the kth moment of a matrix of size n, of a GUE matrix of size n, is a polynomial in n. And this is a consequence of the Wick theorem when you compute expectation of Gaussians. And this is the basic fact behind the theory of topological expansion. So for instance, if you consider this moment, the 8th moment of a GUE matrix of size n, you have a polynomial in n. So, and this has a combinatorial interpretation. If you consider an octagon, there are 14 ways to fold the octagon on a sphere, 70 ways to fold the octagons on a torus, and 21 to fold the octagon and on a surface of genus 2. Now, on the other hand, yes, less attention has been devoted to the same quantities, now not as a function of n, but as a function of k, of the order of the moment. And actually, if you consider these objects as a function of k, where k can be a complex variable, there is a new, very remarkable structure. So the main result is that for the classical ensembles of Hermitian random matrices, the moments, if properly normalized, are orthogonal polynomials as functions of k. And actually, they are not just orthogonal polynomials, they are classical, they are called neoclassical orthogonal polynomials. The precise terminology is hypergeometric. And actually, they are hypergeometric orthogonal polynomials as a function of n2. So as an example, if you consider again the GUE, now of size 4 as a function of k, is a polynomial of degree k. And actually, these polynomials are not just random polynomials, they are maximum polynomials. So there is a nice connection between matrix ensembles, correlation functions, and moments. And there are other interesting facts that are summarized here.
Hi. Okay. I'll just give a brief outline of what I've been doing. So my main question is if Painleve II tau function can be expressed in terms of a Freedom determinant. To begin with, what's Painleve II? It's the equation that we've been seeing. And now the tau function has many definitions, but it is also related to the Painleve transcendent as a logarithmic derivative. Now, to answer the first question, to answer the first question, what is known till now about the Painleve II tau function is that the Ablovitz-Sigur family of functions has a tau function which can be represented as a Freedom determinant. This is the Ablovitz-Sigur family of functions. And the tau function is given as the determinant of the Airy kernel. And now this should be generalized to general Painleve II. To do that, there are some issues with the Riemann-Hilbert problem which are a bit complicated than the previous example. However, I can reduce everything onto imaginary axis. And this is the, I'm sorry, yeah. Everything can be reduced onto the imaginary axis. with this particular Riemann-Hilbert problem. Notice that today in the talk by Professor Ritz, we learned that there is something to do with, these have something to do with the parabolic cylindrical functions. And in fact, these two are given in terms of very complicated functions of parabolic cylindrical functions. And now using the LU-LU decomposition, I can split this contour, the jump on this contour onto 4 parallel contours. Now the advantage of that is that I can write the jump function. I can write the jump function in terms in this form, where f of z and g of z are given in terms of projectors on these spaces, on the respective spaces of the jumps. And this is the formulation. And notice that all these are, everything is in terms of parabolic cylindrical functions, apart from chi1, chi2, chi3, and chi4, which are the projectors. Now, the integrable kernel, which can be formulated in terms of the same f of z and g of z as this. This is a very well-known result. And the tau function is given in terms of this integrable kernel. And what is more is that I can actually link this tau function to the isomonodromic tau function. After a long series of computations, I can give the, so this is the isomonodromic tau function, the J mu tau function. And notice that everything is only in terms of the parameter of the Painleve II, which is S, and nu, which is the constant given in terms of the Stokes parameters of the Painleve II. Thank you.
Thank you. So Alexander, please come. Alexander Gamayun.
Okay. So the problems I'm talking about is about extreme gaps. So people studied, for the random matrices, people know many things about average gaps, like Mata-Gaussian distributions. But I'm interested in the smallest gap and the largest gap. Okay. So, so this. Oh my. So this is okay. Let's just talk this result. So this is the smallest result for COE, and we know. So this. So the smallest gap is n to the negative 4/3. This is the power of the smallest gap of COE. And in 2013, and Benassi and Berger, they proved that the smallest gap tend to the Poisson distribution. And they write down the distribution of the smallest gap. And what we prove? So we prove last year is for C beta E, the similar result can be held. But the spacing, smallest gap spacing is n to the power beta plus 2 over beta plus 1. And the same Poisson distribution is derived. And there's a constant. Is A beta is very meaningful. This is the quotient of the limit of quotient of 1 pound log gas over the 2 pound log gas. Okay. And this constant, so you see, is 1 over 24 is just the same as before, right? So this result, and we also have the proof is used the determinant point process, and the first studied by the Soshnikov, then Benassi and Berger used this approach to study the Soshnikov study for general case, and Benassi and Berger used more to apply it to COE, and they also prove for the GOE in the interior is the same power is observed. So, but in our recent papers, we prove for GOE, okay, it's not determinant point process, it's a thing. So the minimal spacing, I mean the smallest spacing is n to the 3/2, okay, and the same we can also derive the space, the probability, okay. Oh, so how about the largest gap, okay? So 2013, so they proved the largest gap is square root 32 log n over n, okay? But this is not enough. So we proved last year for COE, okay, so we're rescaling it. And we found the limit is the Gambau distribution. Okay.
So, David, Garcia, please come.
Okay, so my work is based on so my work is based on these papers with these guys, and it's mainly about dynamics in classical integrable systems. So roughly speaking, the problem is like this. So imagine you have a soliton solution in your system, and then suddenly some parameters of your system changes or something happens. So this is no longer a solution, and you're interested in what will be a asymptotic form of this profile. How will it evolve? And in my poster, I considered two problems. So one is nonlinear Schrödinger, both attractive and repulsive at finite density. And here, the quench parameter is eta, and depending on eta, we have these beautiful pictures. So in attractive case, we see this what we call instanton breathing and ballistic spreading of profile. While for repulsive, we see this what we call anti-light cone effect. So you clearly see separation between solitons and what we call radiation. And in my poster, I tried to give some description of this and avoid the Riemann-Hilbert problem as much as possible. So my second model is basically a Landau-Lifshitz model, which is continuous version of XXZ and classical. So this is basically the dynamics of unit vector in 3D, and it's given with anisotropy along third axis. And as a quench initial state, I consider basically domain wall profile. So you have some spins down in half space, and then some spins up, and then you let it go, and you ask what will happen. And you see that depending on the anisotropy, you have very different results. So it's either ballistic spreading in easy plane case, or some wobbling motion in easy axis. And the most interesting is isotropic, where we see this logarithmically enhanced diffusion. And basically, the dependence on, it arises some interesting scalings, which also relevant for some vortex filaments, and eventually to some Painleve IV equation, which is not really in my poster, but we can talk anyway. So thank you.
Okay, so please, Tristan, please come.
Okay, thank you. Okay, so I will be speaking about some matrix models for the classical groups in their relation with Toeplitz+Hankel determinants and minors, okay? Which is joint work with Miguel Thiers. Okay, so let me consider this kind of integral, which is an integral over the n-dimensional torus of the modulus square of the van der Monde determinant times the product of a given function supported on the unit circle, okay, acting on each of the variables. As we know from several of the lectures of the school, this comes from an integral formula, and it's actually representing an integral over the group of unitary matrices of rank n, okay, of the given function defined with respect to Haar measure. And another way to compute these integrals is as the corresponding Toeplitz determinant of order n, okay, where the coefficients in the diagonals are the Fourier coefficients of the function f. Now, let me ask you what happens about, if maybe you know already, what happens if I remove some of the rows and columns of this determinant. Okay, so I'm considering a minor of the underlying Toeplitz determinant. Here I'm removing the first and third row and second and fourth column, okay? Okay. And as you may, okay, it turns out that considering such a striking of rows and columns amounts to inserting a couple of Schur polynomials into the corresponding integrals, okay, which are indexed by Young diagrams, lambda mu, which are related to the particular striking considered. Okay. Now, if we switch from the unitary group to one of the other classical groups, such as the symplectic group or the orthogonal groups, okay, we actually get an integral of the same form. It's also over the n-dimensional torus. We also have the weight function supporting the unit circle acting on each of the variables, and then we get the modulus square of a generalized van der Monde determinant, okay, which is slightly more complicated. As you may already know, the way to compute these integrals is by means of Toeplitz+Hankel determinants instead of just Toeplitz determinants, okay? If you look closely, you will see that this matrix is from Toeplitz minus Hankel, okay? This particular example corresponds to the symplectic group, okay? And it turns out that if you remove some of the rows and columns of the determinant, what you get into the integral is the insertion of the reducible characters associated to the groups Gn. This may be not so surprising since the Schur polynomials were, okay, among many other things, they are, of course, the reducible characters associated to the representations of the unitary group, okay? The interesting fact here is that if we remove the same rows and columns in this setting as in the unitary setting, we get actually the insertion of the characters associated to the same Young diagrams, okay? So if I remove, again, first and third rows and second and fourth columns, for instance, I will get the characters associated to the same lambda and mu, okay? And okay, let me just briefly sketch some of the advantages of this approach to computing these kind of integrals. Well, maybe the first one will be, yeah, I am twisting group integrals, which are already an interesting object, by the insertion of irreducible characters, okay? Does that mean I have 15 more seconds, or?
Yes.
Okay, then we are also able to, okay, we're also able to obtain factorizations for partition functions for series with unitary symmetry as products of partition functions with different symmetries, okay, as you can see there. We are able to expand determinants of the aforementioned Toeplitz+Hankel matrices as sums of Toeplitz minors, okay, and then we also apply this to Chern-Simons theory, okay, where we can compute some of the observables of the theory. Okay, thank you.
Hello, my name is Tristan Gauthier. I'm a PhD student in ENS in Paris, and I'm going to tell you about a kind of a very simple problem about the survival probability of a Brownian motion under a moving boundary, and see how an interesting generalization of this can be understood in terms of a physics problem. So if you take just a Brownian path under a moving boundary, there's several, it's a well-known problem, well-studied, and there's several different cases that happen. If the barrier is very slow, so consider, for example, a fixed barrier, or any barrier that's slower than square root of t is going to be very slow compared to the Brownian. Well, then the survival probability, the probability that the Brownian path has not touched the barrier, goes down as 1 over square root of t. It's a universal exponent. If the barrier is faster than the Brownian, well, the Brownian has some probability to not touch it at infinite time, and it goes to a positive constant. And the interesting case, of course, the critical case when the barrier goes as w square root of t, and then the survival probability goes down as a parallel with a non-universal exponent that's interesting and depends on continuously on w. And the idea then is that how does this problem work when you take n non-intersecting Brownians, and the survival probability now is the probability that you haven't touched the barrier and also you've stayed in the Weil chamber. The Brownian have not touched each other. And this has an interesting answer in terms of a physics problem, because you can basically change your problem from these Brownians to a stationary Ornstein-Uhlenbeck processes with a fixed barrier, and this can very interestingly, with the non-intersecting probability by Carlin-McGregor and determinant structures, go to a quantum problem where you have n fermions in quite a simple potential with a hard wall at W. And so this quantity, this survival, this decay parallel becomes very simply the ground state energy of your n fermion system in this Hamiltonian. So have more technical stuff in the poster if you're interested. And there's interesting applications to random matrices through the Dyson's Brownian motion. Of course, that's non-intersecting process, and other problems. Thank you very much.
Okay. So thank you. So in my poster, I will talk about some applications of random matrix theory and more generally determinantal point process to systems of fermions. So basically, if you take a system of non-interacting fermions, then you can compute or obtain what are the single particle wave functions. And if you take the case of 0 temperature, you have n lowest energy levels. And if you want to compute the ground state probability
of the position of the fermions, then it's just given by this modulus squared of Slater determinant. And this squared modulus can be placed in terms of this kernel. And it turns out that if you take a non-degenerate ground state and using the orthonormality of the wave function, you can prove that this is a determinantal point process. Then you obtain all the p-point correlation function, for example. And we are particularly interested in occurrences where the potential leads to an exact mapping with some problems of random matrix theory. So we identified a couple of instances where this is the case. So many instances in one dimension and one particular instance in dimension 2, which is the first time that we could do that. And more generally, we extend also this kind of kernel known from random matrix theory to these higher dimensional point processes. So if you are interested in this, come see my poster.
Hi. So we're going to speak about statistics of Toda lattice, but first of all, what is Toda lattice? It's a well-known Hamiltonian system with the following Hamiltonian, and moreover, it's well known to be integrable because it has a Lax-Pierre formulation with these variables which are called Flaschka variables, and they are not it's not a canonical change of coordinates, but is a really nice view of the system in this way because we know that it is integrable in this way. Moreover, can be integrated through a spectral problem. So we have to introduce a lot of spectral variables, really difficult to solve, but not that difficult, but actually quite. And we know that we can express so the A and B through the lambda and the mu, which are the eigenvalues of L, which are constant, so they don't depend on time, and the mu, which are the eigenvalues of M, which are obtained by erasing the first column and the first row. And moreover, they are interlaced. But we want to study statistics. So we have to put the Gibbs measure on this on the phase space, and this is the Hamiltonian of the system with parameter beta, which is the inverse of the temperature, and this is the normalizing constant. This function is not the Barron's G function, but is the Mayer G function, and it was quite a pain to get this result. Actually, it's not that easy. And so, what one can study? Well, since everything depends on lambda and mu, we would like to know their distribution. So the limiting distribution of L eigenvalues, which is a random matrix problem, and the gap distribution, which is, again, a random matrix problem. Moreover, we can look at problem like in the thermodynamical limit, so beta fixed, or beta going to infinity, so temperature going to 0. And we can get pretty different results. Till now, we are able to prove that the distribution, where beta is fixed, has no compass support. Instead, when beta goes to infinity, it converges to the R' distribution, which is this one. Instead, the gap, the gamma j, goes to 0 in both cases with different decay. And the expected value of the L1 norm of the gap here goes to infinity, like the square root of the logarithm. And the other case instead goes to 4, which is the limiting distribution here. And these two have two pictures of the distribution of the eigenvalues, actually. This one is the R', and this one we have no clue what can be. Is nothing that can be done till now. So thank you for the attention.
Yes, I would like, first of all, to thank the organizers for this nice school. And I would like to present my recent work with Professor Dubrovin, where we developed forward and inverse scattering transform method for a class of unbounded solutions of the Korteweg-de-Vries equation. Namely, we consider Cauchy problem for the Korteweg-de-Vries equation, and initial function from that class which we consider grows as third root of minus x when x tends to plus and minus infinity. And we show how to solve the Cauchy problem with this initial function. For some other cases of initial functions, this problem is already well known. And everything is based on the Lex pair representation. And if you think for which kind of initial functions you can apply this, this Lex pair representation might be useful, then you realize that's in the case when the initial function is asymptotic for large x, for x tends to plus and minus infinity, to some exact solutions of the Korteweg-de-Vries equation. And those examples of exact solutions are zero, constants, the so-called finite gap solutions, and the famous time-dependent solution to the second member of Painleve I hierarchy, U of xt. And many people contributed in different aspects, including Boris Dubrovin, Andrei Kapaev, Alexander Itz, Tamara Grava, Irina Yegorova. So what we are doing, we further extend the inverse K-trend transform method for the class of initial functions, which are perturbations of this function U of xt. So we take it at some fixed time t0, perturb, and then take this perturbation as an initial function for the Korteweg-de-Vries equation. And then we show what can be analogies for the Jost solutions, how to define analogies of transmission coefficient, reflection coefficient, and then how to solve the inverse problem. Given spectral functions, how to reconstruct the solution of the Korteweg-de-Vries equation. Oh, still some time. Yeah. Great. I'm fine. If you're interested, you can.
So, Leslie Molag, please come.
Hello, my name is Fatana from Concordia University, Montreal, Canada, and I'm going to introduce you my current project about Calogero-Painleve systems and their corresponding multiparticle quantized Hamiltonians. So since the demonstration of Painleve equations, they came to the interest for a lot of mathematicians because of their properties, and one of the amazing things about these equations is their interaction with Calogero system, which was introduced at first by Takasaki. This brought a lot of new ideas for research in this area. So in my work, I actually at first considered the Schrödinger equation. I generalized this equation to the case of M particle and introduced the integral solutions to this equation for quantum Painleve equations. And then I actually consider the Hamiltonian operators in the Calogero-Painleve system, which are in the form of trace of a function, and apply a quantization to these Hamiltonians to see whether I get the same quantized Hamiltonian operators. And to do that, I use some group actions and Harish-Chandra homomorphism. So as I told you, I first actually had Nagoya's paper as a reference. He introduced the Schrödinger equation for the case of one particle, and well, I generalized that to the case of M particle, and oops. Yeah, oops, okay. So, hello. This is the equation for the case of M particle, and this psi is the integral solution, and as you see, these theta j functions, which are called master functions, differ from different Painleve equations 2 to 6. So these constants here in these functions must satisfy these properties if we want to have this equation to be satisfied. So out of these computations, I obtained these Hamiltonians. We can go through details for anybody who is interested during the poster session. But these Hamiltonian operators will give me the same operators if I consider n equal 1 as in Nagoya's paper. So considering this, my supervisor Marco Bertolla, together with Mattia Cafasso and another their colleague, recently published a paper. They introduced the isomonodromic formulation for Calogero-Painleve system, in which they introduced the Hamiltonian operators in terms of the trace of a matrix. Here P and Q are matrices, so what I'm doing now is actually applying quantization to those Hamiltonians to see whether I get the same Hamiltonians that satisfy the Schrödinger equation. Thank you for your attention.
Giulio Ruzza, please come.
All right, so I will tell you about the conditional measure of the Bessel process. For that, I need to introduce the concept of rigidity. So rigidity means, so suppose we have a point process, then rigidity means that if we know the position of the points outside a certain interval, then with probability 1, we know the amount of points inside that interval. So here's an example where you see that the red points, those are frozen, those are fixed. And then we can actually consider a measure on the interval that we've chosen. So here it's 0 to r. And that measure is called the conditional measure. And it's a recent result by Gauche that the sign process, so the determinantal point process with the sign kernel, is a rigid process. And it's an even more recent find by Alexander Buvetov that that's also true for the Bessel and the Airy process. And in particular, he proved a nice result that these three determinantal point processes are actually orthogonal polynomial ensembles. And he posed an interesting question, which is what happens when we let the interval that we consider grow to cover the entire space? So that's the limit of r tends to infinity, an example that we had. And quite recently, that question was answered by Arno Kuilers and Erin Minya Diaz for the sign process, and they show that that it converges back to the original process on the entire line. And what I proved together with Marco Stevens is that this also holds for the Bessel process. So the conditional measure will converge back to the original point process. And I will briefly tell something about the approach. So yeah, we have to know how a typical configuration of the Bessel process behaves. And we actually approximate our orthogonal polynomial ensemble by another one that has a more convenient weight, namely convenient for Riemann-Hilbert analysis. So that's what we do. And then in the end, there's a pretty nice technique by Lubinsky to then find what this means for our original orthogonal polynomial ensemble. That's it. Thank you.
No. So, thank you for giving me the opportunity to present this poster and to give this short presentation. This is work under supervision of Professor Marco Bertola at SISSA. No, the other way. Okay. So, in many cases, you can treat a matrix integral in a formal way. Matrix integral that depends on parameters, like so essentially as a formal power series, and the coefficients in these cases have an important interpretation of combinatorial objects or enumerative geometry invariants. It is used to consider actually the coefficient in the expansion, this formal expansion of the log of z. If you know from combinatorics and maybe quantum field theory, this choice of choosing logarithm of z is because we want to consider connected objects. But this will become clear in the examples. So one is a very famous example of the Gaussian unitary ensemble, which we already met, and the combinatorial objects are the ribbon graphs, much more recent and actually work of, other way. Okay, and work of in other posters by Cunden and other authors. And the Laguerre unitary ensemble partition function recovers strictly monotone Hurwitz numbers. And another important class of example is given by generalizations of the Kontsievich matrix integral, where here the situation is a bit more subtle, namely the parameters t can appear only after a suitable limits that you do, often in a formal way. So I'm not doing this properly, but maybe the main question and the main answer, main result of this poster, is there a way to compute effectively correlators of such models? Well, very recently, formulae of this kind have appeared for the correlators of these models, and you will find many of them in my poster and also in the follow-up talk by Massimo. And yes, and apply to the examples I had shown before. So maybe just a word, because I think I don't have time, but this is the main conceptual result and also the technical tool that we use. The conceptual result is that we are identifying actually the matrix models and the dependence on parameters as tau function of isomonodromic system that we have met, isomonodromic system we have met this morning with Professor Ritz. And this gives actually some possible application which I list here, then we can more or less stop.
Oleg Sienkiewicz, please come.
Okay, so I'm working with Giulio, from whom you have just heard, and on idea and with the support of Professor Tamara Grava to try and relate the LUE correlators with the double monton-Hurwitz numbers. So we'll show you some the procedure we are following. So we're interested in the following 2x2 ODE with the matrix in slide, which has by solution exactly the Laguerre polynomials and their Cauchy transforms, the monic Laguerre polynomials. And if we look at symptotics at infinity, we can safely expand this solution outside of the real axis and actually get an explicit solution for the yx, and the matrix theta x takes care of the monodromy of the associated system. So our goal is to look at the LUE partition function. And from the work of Bertrand, Arnaud, we know that the exponential weight is nice enough to use the Jimbo-Mimo-Ueno formula, and in this way to recover the one-point correlators associated through the Jimbo-Mimo-Ueno formula, and actually we can compute it explicitly. If we define the R in this way, then the following hold, we can take the following series for the S1, and we actually are able to compute it just looking at the trace of this matrix AR. R is just given by the matrix Y, which we already computed explicitly. So this gives us an explicit formula that actually agrees with the literature. So the final goal is to compute the double monton-Hurwitz numbers, which have been found recently by Cunden, Dahlqvist, and O'Connell to be related to the LUE. In particular, from what you've heard from Giulio, we know that knowing the S1, the one-point correlator formula, is enough to compute algorithmically all the multi-point correlator formulas. And in this way, we can try and compute explicitly the double monton-Hurwitz numbers, which are coefficients of this genus expansion for the cumulants, which are not exactly the multi-point correlator, but are really similar and can be computed in terms of. So our future goals is to adjust this and actually give closed formulas or at least an algorithm to compute the double strictly monton-Hurwitz numbers, and then doing more or less the same thing, just taking the expansion at 0 of our isomonodromy tau function and relate to the double, not strictly, monotone-Hurwitz numbers, which have a genus expansion of the same type that you can find in the same paper of Cunden, Dahlqvist, and O'Connell. And have a good day.
So, wait a second, it's not mine. Okay, my work is about multi-component Curie-Weiss model. I do it with my PhD supervisor Antonio Mora and also our collaborators Adriana Vara and Elena Agliari. So, Curie-Weiss model is famous for its hysteresis properties. It explains ferromagnets. And multi-component Curie-Weiss model is just a binary spin model on a complete graph. It's like on this picture, it's two-component model. So you have two separated Curie-Weiss components connected with each other, fully connected with some other coupling. You see the Hamiltonian here, so Hamiltonian is quadratic. The model is fully solvable. The way we solve it is by deriving the equations, PDs on the order parameters. So yeah, we'll skip this. Finally, we get the free energy and the equations of state together with the stability condition, which is the positive definiteness of Hessian of the free energy. So in this model, you get multi-stability. Like in single Curie-Weiss model, you get maximum B-stability. Here you get up to 4 in two-component model. And the number of stable states we suppose is, it's easily provable. It's 2 to the power of number of components. So I actually want to show you a cartoon. That you see is so-called general fault. So we analyze two-component system using witness catastrophe theory. So you see this so-called cusp points. It's these cusps. They correspond to critical points, and the solutions they appear and die on the general fault. General fault defines how many stable and unstable solutions we have for a particular configuration. And if you want to know more about this, come and see me with my poster.
Thank you. So, Yekaterina, please come.
Hello, my presentation is based on joint work with Yashin Amir in Lund University and Namgyu Kang in KIAS. And our model is basically the random normal matrix model, which is a two-dimensional Coulomb gas at a specific inverse temperature, so determinant case. So we consider n-point charges on the complex plane influenced by an external potential n times Vn. Here, Vn is an n-dependent potential perturbed by the logarithmic term. And we consider the system with respect to this Boltzmann-Gibbs distribution. And then this gives the two-dimensional Coulomb gas in presence of an extra particle with charge C at the origin. So we want to know the large n behavior of the system. And globally, with a sufficient growth condition, the eigenvalues condensate on a compact set. We call the droplet as n tends to infinity. We studied a case when the singularity is in the bulk, in the interior of the droplet. And we want to see the effect of insertion. So we are interested in the microscopic properties of eigenvalues at the singularity and difference between the one-point functions with and without insertion, and some central limit theorem for the logarithmic potential. The main part of my poster is devoted to bulk universality for a class of external potentials. Our potential is the sum of radially symmetric function, whose dominant term is mod zeta to the 2 lambda, and harmonic potential. Then we obtain the scaling limit at the singularity. We show the limiting correlation kernel of this rescaled system at the origin is described by the two-parametric Mittag-Leffler function, which depends on lambda from the dominant term and C. So if you are interested, please come to see my poster. Thank you very much.
Bonjour. My name is Ekaterina Shotka, and I will talk about semi-classical approximations for the spectrum of the subcritical Harper operator. This is a joint work with Alexander Fedotov. So we study the Harper operator acting on L2 by this formula. H is a shift parameter, and lambda is a coupling constant. This operator arises in solid-state physics, in particular when studying an electron in a crystal placed in a weak magnetic field. And so it comes from physics. And why is it interesting for mathematicians? Because at least for two reasons. First, for irrational H, its spectrum is a counterset. That is, it's closed, nowhere dense, and has no isolated points. So it's kind of fractal structure. And second, this model is an example where the phase transition takes place, depending on the parameter lambda, on the coupling constant. So my goal is to describe a geometry of the spectrum, its thin structure. And in semi-classical approximation, as H tends to 0, we describe the spectrum asymptotically. So this is my result. There are two different spectral modes. So the spectrum is divided into two parts. On the first interval, the spectrum lies on the intervals, on subintervals of order H, separated by exponentially small gaps. And on the second interval, the spectrum lies on exponentially small subintervals separated by gaps of order H. So there are two different spectral regimes. And these two different regimes, they are related to two different possible two different possible types of isoenergy curves that is defined here. And this is shown here, and I will be happy to explain everything in details, especially these pictures and these contours, gamma x and gamma p, and give exact statements of the theorems. So thank you very much. Merci beaucoup.
Thanks a lot. Thank you. So we are at the end of this nice series of short presentations by 21 of our young colleagues. So please join me in thanking all of them and their mentors for this beautiful work.